Here, so question is, you are given n plates and you have to fill every plate with a single rose. Rose can be of red color or white color. So there are two kinds of roses, and you can say you have infinite supplies of both roses. You have to tell that how many total ways are there to place them. The condition is two white roses cannot be put together. So if you observe here, if there are three plates, on first plate you can put red rose, second plate you can put white rose, third place you can again put red rose. So if you look at all these arrangements, there are total 5 arrangements. Similar way, can you work out if you have 4 plates, you have to put red and white roses into 4 plates. How many ways do you get? Work it out on your notebook, and just once you have calculated the answer, just type your answer in the chat. How many ways are you getting if you have 4 plates? Okay, so four people got answer of 8. Let me put that here. Okay, everyone got 8 for this? Anil got 7.
I got only 7, yeah.
Sure, let's see. Let's see what are those arrangements. So can I say it's RRRR, RRWR 2, RRRW 3, RR.
Yeah, now I got 8. Yeah, got it. I missed 1.
8.
RRR.
Perfect. So basically there are 8 patterns that are going to be there. In fact, this problem is kind of a twisted form of a question. If you look at binary patterns will have zeros and ones. So essentially, if I just see R as 0, W as 1, so these are binary number wise, this is 4 zeros, this is 0, 0, 0, 1. So essentially, I should be keeping as W, this is WR, this is 1, 0, this is 1, 1. 1, 1 I cannot keep because two W's will come together, so that pattern will be ignored. So this is 1, 0, 0, RW, RW, 1, 0, 1, 0, 0, 1, 0, 1. What are the other patterns? 1, 2, 3, 4, 5. I have written 5. W triple R, WR, RW, WR, WR. Then, is that it?
Yeah, that's all. 8.
Okay, that's all. Okay, so these are the 8 patterns that we got. Now, if we have to solve this problem programmatically, if this is the programming question, how do you go about solving this? Let's go ahead with that and let's try that. Okay. So first of all, I told you that we will be using left side of recurrence. For now, you may ask, like, why am I thinking recursive? For that, you trust me that we will go ahead and solve this problem recursively. We'll define this recursively. Gradually, you will understand all this. So first of all, left side of recurrence, what is it that we are trying to achieve? And what will be the left side of recurrence? So will it be fair if I say I want to find ways of n? That is my recurrence. If n plates are there, how many ways are there in total? White rose, red rose is a fixed thing. N is varying, right?
Yeah.
Okay. I'll say its interpretation is, it is number of ways to arrange n roses, or n roses, you can call it n plates, such that no two white roses are together. That is what I'm just describing left side with. Okay. Now, if we have to go with that intuition, will it be fair to say there are some arrangements that will start with R and there are some arrangements that will start with W? There is no third possibility.
Yeah, that makes
sense. That makes sense. Okay, so we are saying now, in order to go ahead with our formula, we are saying total ways for n is nothing but it is how many ways are there, ways when R is starting point, or ways where W is starting point. If you get this count, what will be the final answer? How do we link them? Let's say somehow you got how many of those patterns start with W. Sharik says sum of 2.
I think that would be just simple addition.
Simple addition. Okay, 2 people are saying it will be addition. Basically count how many patterns start with R, how many patterns start with W, just add them. That is your final answer. Because everyone agrees with this, it will be a simple addition of count how many patterns start with R, how many patterns start with W. Okay, fair. So it is addition of those two. Okay, now let's try to express this thing. How many patterns start with R? Let's try to express that kind of as a sub problem, as a recursion. For example, if I say ways of n is equal to, if R is the starting point, how many places are left now? If total places were n, how many places are left now?
n minus 1.
N minus 1. In those n minus 1, even if we ignore what we have filled, can we say it is same problem? How many ways are there to find in how many ways we can fill roses, W or red roses, remaining n minus 1 plates? Is it smaller instance of the same problem?
Yeah.
Yes.
Yeah. Okay. So this is all the ways that are starting with R are coming like this. Same way, plus if we start with W, we again know there will be n minus 1 places left. But in this n minus 1 places, are we free to fill any W or R? Is that
No,
freedom there? No.
If we fill a W, then it has necessarily to be followed by an R.
Okay, so here Prakash is giving us some idea. He says if you start with W, then you cannot go with W only. Your starting point has to be WR. Does everyone agree with that?
Yes, because no two whites should be single together.
Because if you start with W, then next has to be R, next cannot be W. Now, after you have put R here, can you fill anything in remaining n by 2 places?
Yeah.
Yes.
Yes. Okay.
Not
You know
every.
what this?
The
Go on,
next
go on.
place you can keep anything, but the remaining places should be like alternative, right? Or something.
No, again, it's a smaller version of the same problem. You have to fill n minus 2 places with white and red roses such that no two white roses come together.
Okay, yeah.
So it is now the space is n by 2, but the constraints and the actual problem still remains the same. You are free to choose anything here. You can again choose R or you can choose WR again. Is that correct?
Yes,
Yeah.
yes.
Okay. You know, this will come out to be the ways that start with R is nothing but ways of n minus 1. Plus the ways that start with WR is nothing but ways of n. Have you seen this formula earlier, this recurrence earlier? This is a well-known recurrence relation.
Fibonacci.
This is Fibonacci, yes. And you know this problem is Fibonacci problem. But see, the problem looks very scary. Let's see, let's validate whether this is really Fibonacci. Yeah. Any question?
I have one question here. Like, how can we identify this problem can be a Fibonacci? Like, because this is not something straightforward, right?
Correct. So that is where I said initially that trust me, we will go and refine recurrence. It is more practice that you do. Usually we say problems which require count how many ways are there, or which require find the maximum ways of achieving something, minimum ways of achieving something. These three category of problem we can identify, they might be related to DP.
Got it.
Yeah, so it will come with experience. It's not like, that's why I said, like, I'm giving you this idea and saying let's work out recurrence, and I did not tell you like why we are working out recurrence. So next time if you see a counting problem, one trigger should be there in mind. Hey, can I try like a DP problem? Okay, that we will see. Today's goal is to go a little more elaborate this space and understand. So first we have seen this is a counting problem. For now, short answer to your question is, since it is a counting problem, we will think of, can we define the relation recursively?
So can you explain like how we concluded to the final equation that you've written from R and WR scenario?
Yes, I will conclude that. So see, now we will draw actually our tree. So we have, let's go ahead with 3 spaces. 3 plates are there. N is 3. So first you said I have two choices. I can either go with R in the first place, or I can go with WR in the first place. This is clear why R and WR are the starting points.
Yeah.
Okay, so when you come left side, your R is filled already. You have two more places to fill. When you have filled WR, how many more places are left?
1.
1.
One. So now let's continue and let's try to figure out this problem solution below. How many ways are there to fill two places? Again, you will go with R as one choice. So left side will become RR dash. Do you agree?
Yes.
Or you will go with
W.
RWR.
Yeah.
Okay. Now, since there is one place, you can choose to fill anything, RRR or RRW, right?
Yes.
So if I ask you, there are two ways to fill one place because there was one place empty. Here, if you look at, we were solving a problem of n is equal to 1. If n is 1, there are two ways. Here you are solving a problem of two size, and problem of two size has three solutions here, which was RR, RW, RR, WR. So here, up to here, you have got three solutions, correct? Three solutions are there which start with R. Do you agree? The circled ones
Yes.
I'm counting. Let's go to right side. How many solutions are possible here?
2.
Two, because you will fill WRR or WRW. Basically, here you are saying there are two possible ways of filling. Here you are saying there are three possible ways of filling. 3 plus 2 is your final answer, correct?
Yeah.
Correct.
Okay, so we are
let's-
just subdividing the problem into n-1 and n-2 sizes.
Absolutely.
R and W are just for our convenience that we are keeping track.
Absolutely. Absolutely.
Got it.
Yes.
And now this
So
makes
because you are saying since R is fixed, we don't have to worry about R. Whatever arrangements are possible for these two, those are the arrangements that start with R for us. So those were three arrangements. So it left side is actually solution of n-2, right side is solution of n-1. You are adding them. That is how we came up with the recurrence. So that is how I said ways of n-1 plus ways of n-2. Okay, so essentially if we formalize it now, I said ways of filling n space is equal to ways that start with R plus ways that start with W. This we reworded it as Prakash helped us visualize that. Prakash said ways that start with R. He said visualize the second thing differently, ways that start with WR. The benefit of rewording this is we can actually come back to original problem. And those ways will be, since one place is already gone, this will be ways of n-1 because R is fixed and we are left with remaining n-1 places. And in second option, since WR is fixed, we'll go with n-2 places. That is how you will go ahead and write this recurrence. Okay, these three lines help us visualize it clearly.
Yes, sir. So here just one question. If we have to just calculate the maximum, like count or maximum, as you said, so we'll be going with DP. But suppose we have to print all the paths or print the number of ways or sequence, then we'll go for backtracking, right?
Yes, that's true.
Okay. Yeah.
Those are printing problems, like print how many ways are possible. Here I said counting problems or minimize optimization problems. So two categories of problems I'm specifically saying for DP, counting or optimization. And optimizations are the ones find minimum ways of doing something or maximum. In fact, if you correlate the previous problems in grid DP are solving, find the min cost path in a matrix.
Correct.
So we have done these problems. In fact, you have counted in grid DP also, you have counted how many ways are there starting from 0, 0, reaching the last cell if there are some hurdles in between. So you have solved both kind of problems already. So you know now, okay, those are the problems we are dealing with in DP.
Yes, sir.
Correct? Okay. Sometimes there can be one more category also. It's Boolean answer problem. Boolean answer is there any path whose sum is 20? In grid DP, we have not put those problems. We will do them when we come to subset DP. Is there any path? So in fact, I'll say these three should be the broader category of all the DP problems.
Okay.
Okay. Yeah.
Yeah.
Okay. Now you may say, okay, this was you cheated us. You may say to me that I cheated you because I knew the solution. I'm telling you the solution. But how is there any intuitive way to attack this problem? There is one more way, harder way. It's like hard learned way, but we can try that also. So I'm just giving you, pausing this for a moment. We have come up with the recurrence, but I'm taking you through one more journey also. And that journey is hard work. Just work it out on pen and paper and just see. So what we will do, we will start gradually with smaller case. For example, if there was only one plate, let's fill out a manually answers. If one plate was there, how many ways are there? Tell me, to put white or red roses. For one plate, two. And those two ways are nothing but white or red. Okay. If n is 2,
3
3,
Three.
which are
RRW RRW.
RR, RW, WR. That's it.
Yeah.
If n is 3, how many ways?
5.
5.
Okay. 3 so I
5.
had given also here. So basically we can work that out. This is our 5. And if n is 4, how many ways are there?
8.
8.
8. Work out few examples and just try to see, is this a well-known series? Have you seen this series?
Yeah, Fibonacci.
Okay. Sometimes people do this also, that they write few terms, they come up with some observations. So far our observation says 2 plus 3 is giving you 5, 5 plus 3 is giving you 8, and it's just a guess right now. We don't know whether it is actually Fibonacci. So if it is Fibonacci, what is our next guess? What should be the next
The
number?
next should be 13.
13.
13.
Should be, but we should validate now. Let's come up with all the patterns of 5 size where we want to see whether do we really get 13. If we really get 13 ways of achieving this, then we will say, okay, our observation is right. And Fibonacci, the formula is already known to us for Fibonacci numbers. Okay, so for this, if we have to work out, as I said, white and red I'm not writing. I'll treat white is 0 and red is 1. Okay, Vision, you are already part of the meeting. There's one more user with your name joining. What is this issue? Okay. Okay, so I'm writing all the binary patterns of 5, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1. Or 1, 1 is not possible because 1, 1 should be possible. 0, 0, wait, let me reverse it. W is 1, R is 0. So this is not possible. One pattern cut. 0, 0, 0. All zeros were one pattern. This one is gone. This is 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0. This is also gone. Do we agree? 1 I'm treating as W. I'm just writing binary pattern. 0, 0, triple 1, triple 1 also cancelled. Then 0, 1, triple 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1. This also cancelled. Okay. So next pattern will be 0, 1, 1, 0, 0, cancelled. 0, 1, 1, 0, 1, cancelled. 0, 1, 1, 1, 0, cancelled. 0, 1, 1, 1, 1. This also cancelled. So these patterns are not the patterns which we care about because W's are coming together. Then you start with 1, 5 zeros, valid. Okay. Then we go with 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, cancelled. 1, 0, 1, 0, 0, 1, 0, 1, 0, 1. 1, 0, 1, 1, 0, cancel. Now, beyond this point, you will see all the numbers will have 2 ones together for sure. 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0, and 1, 1, 1, 1, 1. Okay, so let's count how many patterns are valid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So formula validated that our observation of this might be Fibonacci, we have validated. So, but this required workout. And Not every problem may have Fibonacci series. Some problems may have Fibonacci, some problem may have 4 elements added together. So that's why I said this is harder way. If you're good with numbers, if you can make a table of what are the well-known series, a lot of people in competitive programming do that. They keep the list of well-known series ready with them, and they can identify that is it any one of them. And then there is a formula, recurrence formula, you can easily work out. I guess, is it making sense?
Yeah.
Yeah.
Okay, great. So since this was a starting problem, first problem, we will do a lot of problems on this pattern where you will take different problem statements and you will also try to analyze. So counting DP is something I'll say it has fixed approach. Coding of counting DP is extremely simple. Fibonacci, is it really hard to implement now? Yeah, guys, is Fibonacci hard to implement?
No.
No, sir.
No.
Not at all.
No.
Okay, great.
So, but
So,
here the challenge I feel is identifying that which series this belongs to.
yep. So I will
So,
say,
like
don't go
Fibonacci.
with this approach. I'll say don't go with this approach. Go with breaking the problem down and having a step-by-step approach.
Okay. So, like as you said, like since Fibonacci, we all are aware about it. What are some other series that we should know in order to, crack such problems?
Okay, good question. Acrobately the bashed. Yeah, this is the section I was talking about earlier. If you see
Okay.
Fibonacci, factorial, derangements, there is a formula for derangements also. I think you have done similar question in implementation. Catalan also you have done. And then the arithmetic geometric progression. So mainly these 4, if you want, I can just capture the screenshot of this and see. But this is unreliable method, Abhinil, I'll say.
Okay.
Unreliable as in it doesn't work out very well. And if problem author is clever, he may give you a sequence which you will have tough time figuring out directly. Okay. So in
Okay.
that case also, I can tell you what exactly you can do. So where is our note one?
Sir, I have a question other way around. If we
Sure,
are
go on.
anyways going to work on creating the or writing the recursive relation, so even if we
Correct.
know or don't know the specific series, it doesn't make any difference for us, right?
Doesn't make any
We are
difference.
anyways
Yes.
creating the relation and we are anyways working out on the base cases, so we'll be good there, right?
Yep, you will be good. That's why I'm saying, I'm emphasizing the fact that develop this skill so that you don't have to rely on some hardcode you don't remember thing. This approach will work. Yes, Ruchi, that is certainly true.
Okay, sir.
Okay. So since we are talking about this technique, let's talk about one more thing. Another approach, since I said this is harder way, you have to generate it manually. Another way you can do is you can write a brute force program to generate first 10 numbers in sequence. For example, it is easy for us to write a brute force program which can generate all the binary patterns for you. Like you just run a loop from 1 to, if you are generating 5-bit patterns, you said there are 2 power 5, there are total 32-bit patterns. So it is easy for us to write a program which can go from 0 to 31, convert every number to their binary form, and just validate whether that binary pattern is valid or not valid. So can we write a simple program? So it's like write a program that given n can count how many patterns have 2 or more ones together. It's like brute force program, right? That requires basic programming or bitwise operator techniques. Once you write that program, you give input 5 to that program will generate every binary pattern of 5 digits, and out of them it will cancel out whichever patterns have ones in it. So program will count that for you. So using program, you can count how many such patterns are there for 4 bits, how many such patterns are there for 5 bits, how many such patterns are for 6 bits, 7 bit, and up to 10 you can easily run that program, and that program is helping you count rather than you writing it on pen and paper. And once you have got 10 terms of a sequence, then you can put your thought across this series that I have, can I think of what will be the next term in the series? So that is another technique proficient programmers use to generate these numbers or to generate the series. Okay, but both of them are out of scope for us because we are aware now, we are learning DP, and these problems will have a definitive way of solving if we can develop this thought process. So 3 ways we talked about, but we are mainly going to focus on this particular way, how to build a habit of coming up with recurrences. Okay, cool. So the guidelines that I'm going to say to you is, I think I captured them here, or no, I'll write that. I thought I have pre-written it. So guideline is figure out how many different starting points are there. So in our current problem, you figured out starting points were only 2, and those 2 starting points happen to be R and WR. Okay, and that is how we came up with the recurrence. So this looks very simple, what I'm saying here, but we will apply this technique to next few problems that we are going to discuss. So you will learn how to apply this on your own. Okay, so first I said this, then we went with this, then we have completed our ways of n is equal to ways of n minus 1 plus ways of n minus 2. And then what will be the base case? What is the smallest valid value of n for which you can give answer directly? You can say, hey, this answer I certainly know. For which value of n?
1.
You know, 1. Okay, fair. So what is the answer for 1?
2.
2. Perfect. And if we know the answer for 1, can we calculate 2 using recurrence relation? If I put 2 here, it will be 2 minus 1, 2 minus 2. 2 minus 2 will become 0. So we don't know ways of 0, right?
0, it would be.
0.
Okay, now I'll give you a pause here. Ways of 0 should be 0, or ways of 0 should be 1.
1.
You cannot say
0.
indefinite way. We will not say in indefinite way, but can you tell manually what is ways of 2?
3.
Ways of 2 is 3.
Yeah.
Is that right? Okay, now hear me out. If we want ways of 2 to be calculated by this formula, recurrence only, here you put 2, here will be 1, ways of 1 is 2, then what should be ways of 0? So that this formula works for 2 also.
It should be 1.
1.
It should be 1. Everyone agrees? I will call this as a boundary case.
But that is just for our convenience, right?
Absolutely, that is for convenience. See, you do not have a way of proving if you have 0 plates, how there is one way doesn't make sense. There is no one way possible to put white or red roses together. This is for our convenience. So we tweak boundary cases according to our needs.
Okay.
Yeah, tricky. Okay. Otherwise, Prakash, otherwise, if we do not want to put ways of 0 here, we will have to give these 2 base cases.
Yes.
Yes.
Agree.
So up to you. Either go with these 2 base cases or go with 1 base case and 1 boundary case. Just cut it out. So your formula will hold true.
Got it.
Yeah. So that's the way of thinking. And this is where we have to be kind of little clever, that why we are choosing 0 is for our convenience. We are twisting the rules so that we can code things properly, or we can solve problems quickly. Yeah. So this, why we have come up with ways of 0, 1 is for our convenience, just because we want this to be served by our recurrence. So I'm crossing out this so that you can refer to the notes and you can figure out what it is conveying to us. Okay. Now, where to find answer? If we want to know the answer for n is equal to 4, of course, we will be calling ways with that number. That will give us the answer. Is that making sense?
Yes, sir.
Yep. Okay. So this is our first problem, just to get you started. Ways of n will give the answer.